Okay. At this point, I want to just make a few comments about the this term down here. If you go through the derivation for coming up with this equation, you have to assume steady state flow. Okay, and steady state flow basically says that you have the same mass rate flowing everywhere in the reservoir. Okay, the same mass rate. So there's a so basically these equations are assuming what's called steady state flow. Okay, which says that the mass rate is constant at all radius. Okay, but that means that you have to be feeding gas into the outer boundary. And I was talking with you about in real life you don't have that. You don't feed gas in at the outer boundary. You have a no flow boundary. Okay, and the solutions are basically identical, but if you truly have pseudo-steady state, so that you actually have flow across this outer boundary, so that you can have flow at RE, okay, then that's a what you call a constant pressure outer boundary. Okay, so this is a solution for a constant pressure outer boundary. But the in reality, what happens is that you get this profile that's got this straight line, which should be that straight line. But what happens is that it actually turns over. If you have no flow outer boundary, maybe I should change the color here. Purple or something. So if you've got this no flow outer boundary, what will happen is that this will turn over and it has to go towards zero slope here. In other words, if there's no flow, then dP dr at the outer boundary has to be 0. That's no flow. Darcy says no flow. So you get this little bit of difference in pressure gradient out far away. And I've plotted this on a log scale of radius out here. So the way it ends up being is that if you want to use this is a no flow outer boundary assumption. If you use the this constant pressure outer boundary here, that you basically, by feeding in gas, you keep this, then you have the same equation, but instead, I'm going to have to write this in purple now because it's no flow outer boundary. So I realize there's a lot of equations. So if we have this PE equals constant outer boundary condition, you end up with the exact same equation. But now you have PE minus PWF and reservoir temperature. This would be pseudo pressure. And then you get just log RERW. Okay? Then you end up getting okay? But if instead of measuring or expressing it in terms of the pressure at the outer boundary, if we use the volumetric average, you can rewrite this equation as KH average pressure then you get log RERW minus, be careful here, I think it's 1/2. I think it's 0.6. Oh, something. Close to half. In other words, changing from the outer boundary to the average, volumetric average, it only changes this term here just a little bit, because the log RERW term is around 8 or 9. So you're going to change it a little bit, depending on which one you use. I think these numbers are all right. Okay. And then I think that it doesn't really matter. But the point is that this, using the volumetric average pressure here, what this is really saying is that if you go out for this particular condition to this particular point here, which is at 0.6 RE, this would be the volumetric average pressure. Okay? That's the way to interpret that. Well, the exact number I'm not quite sure about, but it's around 1/2. This equation is correct with the minus 3/4 and using the volumetric average pressure for a no flow outer boundary, which is practically what you actually expect to have. So I just want to kind of let you know that the fact that you have this term here is related to it's because you're using this no flow outer boundary and because you're using the volumetric average pressure in the driving potential. Okay, so that's where the 3/4 comes from. Now what's much more important than that is and of course here, instead of pressure, you should really be using, if it's gas, pseudo pressure for all of these. Okay. Now, most of you people are wanting to become drillers, apparently. And one of the notorious things about drillers is that when they drill with this heavy mud to avoid a blowout, to avoid losing their jobs and lives. And as a consequence of that, the permeability near the well is often damaged, okay? Because you get this mud kind of filtrating into the rock, and it lowers the permeability. Okay? And so if you were to look at, for example, as a function of radius, if we were to look at permeability as a function of radius, go it that way. The background permeability might be this, let's say 10 millidarcies. And then in this region near the well, because you guys have been drilling, might look something like that, where this is 1 millidarcy. Okay? Might be 0.1 millidarcy. It could be 5 millidarcies. Okay? But it's because of this drilling, and it's usually localized near the wellbore. And because of this lower permeability, this is our damage. Okay? What's going to happen to the pressure drop? Well, it's going to be the same here, but then when it comes down in this region here, it's going to have a slope 10 times steeper. Okay? So I'm not going to go from 10 to 1, because that 10 times steeper is a lot steeper. Well, maybe I guess I could. Maybe I'll go to, instead of 10 to 1, I'll go 10 to 2 or something. Okay. So then what's going to happen is that this is going to have a slope in this region here 5 times the slope of the rest of the, throughout the rest of the reservoir. Okay? Because the slope is proportional with 1 over k. Right? Bigger the k, the flatter it is, the less pressure drop. So we've got a slope here that's way down here. So in reality, what's going to happen in this well is that we're not going to be flowing with this bottom hole flowing pressure, but we're going to be flowing with this bottom hole flowing pressure. And I'm going to put it in terms of, okay? So we've got this extra pressure drop because of the damage near the well. Okay? So this is extra pressure drop. And because it's typically a positive, it's an extra pressure drop because it's a damage, the industry has come to call this damage, this extra pressure drop, a skin. Okay? Okay? So that's what they call it. So you're getting this extra pressure drop due to a damage skin effect. Physically, this is kind of how it looks. In reality, the way we model it in the equations is that we let this thing just continue going down, and we just assume that it all happens at the wellbore. Okay? So, physically, this extra pressure drop, that we call skin or damaged skin, occurs from the damage radius into the wellbore radius. Okay? But in our rate equation, we basically say that the delta P skin occurs at RW. Just bang, all of a sudden it just hits. It doesn't really matter, but it's the way the equations are formulated. Okay?
This is because of we don't know what is RD.
Well, you don't know what it is, you just know there's this extra pressure drop. And you don't really care necessarily how far out it goes, you just know there's the extra pressure drop. And so to simplify things, we just make the assumption, we write the equation so that it is as if nothing happens here, but then all of a sudden it drops down at the wellbore. Okay? It's just a mathematical trick, but you get the correct extra pressure drop. And you guys remember extra pressure drop means extra cost. Okay? Or in this case, then, you know, if you want to produce the same rate, you have to draw the pressure further down, and eventually you'll lose money because of that. So the way that we rewrite this equation to include the skin effect here. I'm just going to cheat a little bit. Okay. To take into account the skin effect is what we do is that we add a term S here. Okay? And this is because log RERW, that's dimensionless, right? 3/4 is dimensionless. So this has to be a dimensionless quantity. Okay? That we call the skin. And it's basically equal to the pressure drop, what we call that actual pressure drop, which is the PWF, and this has to be done in pseudo pressure if it's gas flow. So assume pseudo pressure everywhere. Because of gas. I'm just going to write it with pressure, but you can assume. Okay. So this PWF, I'm going to call this here ideal, or skin of 0. And this is the actual PWF. Okay? So this is this ideal skin of 0 minus the actual PWF. That's this extra skin. So we can that's what we call delta P skin. So this dimensionless is equal to the true times, for gas, I guess I'll go ahead and put it in here. There. KH over Q gas reservoir temperature. And since we're using units here, this 0.703. Okay. Okay, so that's the dimensionless skin effect. Yeah.
But if we stimulate the
We're not stimulating it, we're just damaging.
only damaging.
We're only damaging. Okay? So we can then put this skin here, which represents some form of damage. Okay? Okay. Now, the magnitude, what is the magnitude of, I'm going to call it drillers, just call it the way it is, drillers damaged skin. Okay? That can be on the order of 0 to 5 to 10 to 50 and more. Okay? The first wells drilled in the Troll gas field, they had damaged skins in the hundreds. Okay? In the hundreds. Now, because this quantity here, the normal flow without any damage, is on the order of magnitude 8 or 9, or I'll just say 8. Okay. What that says is a damaged skin of a value of 8. A damaged skin of 8, which is not unusual. What this rate equation, what it says is that how much will the rate decrease if we have a given pressure drop? Okay, we're controlling the choke at the surface, right? And we get this given pressure drop, and we got a well that's damaged just with a +8 skin. How much less rate is it going to produce than if you had no damn driller's skin? Okay, if the drillers didn't screw up the well, how much more rate would you have? If your actual well has an 8 skin, it's producing 1,000,000 cubic meters per day. Big well. Okay. For a given drawdown. But if the drillers, if we did something to get rid of what the drillers did, the completion engineers, these are production engineers, by the way, they get the glory. Okay, they get to clean up the job from the drillers. If I went in and I got rid of this permeability reduction, okay, here, what would the well make? 2 million standard cubic meters per day instead of 1 million. Okay, because if what is actually producing is 8 plus 8, right? Whatever it is, and you're getting 1,000,000 cubic meters per day here. If I get rid of that 8 that the damn drilling engineers gave us in the form of a skin, we just go in and put some acid or clean it up, get rid of that permeability reduction. The well now produces 2 million standard cubic meters per day. Okay? And you can start seeing that it has a big effect. So this skin here is an important quantity. And there are many, many different skin effects. At the top of the list, which is the most common, is, I'll just put it, drillers damage. We might let them off because when we go in and do the completion of the well, maybe the drillers did a good job, but when we're going to complete the well, we're going to perforate it. We do something that we got stuff that goes in, and when they perforate the well, they do it in a bad way. So you got completion damage. S is greater than 0. There's some other kinds of non-ideal effects that, in the context of this equation, give you kind of damage. If for example, your reservoir is like that, your well is like that, and let's say that we only perforate the top 10% of the reservoir. Okay, we only shoot holes in the top for whatever reason. Maybe there's water down here. So what's going to happen is that the gas down here, to get up into the well, it's going to have a flow path that looks like that. Now this gas is not affected, but all this gas is, so you get this converging effect around the perforations. Okay? It causes extra pressure drop. Okay? So you can have flow geometry damage. Now these can be large. These can go up to 10 to 100. This flow geometry damage is typically not more than maybe 1 to 10 at the most. 10 is a big effect, but okay. Another example of flow damage, which is important to the North Sea, is the first field, the Hewitt field I was telling you about. Vetkovich worked on in the 60s. Hewitt field looks something like that. Actually, there's several sands, but each one has its own shape. But it's very high permeability, 1,000, 2,000 millidarcies, 1-2 darcies. Okay? Gas, low viscosity. So the original development plan, some of the operators wanted to put 3 because it's spread out. 3 platforms. 3 platforms, early platforms, first development in the North Sea, going to be big money. Okay. So Vetkovich went in and they looked at the seismic and the geology and everything, and it looked like just blanket sands. Okay? There was no reason to suspect faulting or breaking up or anything. So what they basically went in and did, they said, what we're going to do is that instead of those 3 platforms, we're just going to have, I think it was 1, maybe only 1, maybe 2 platforms. Let's say 2 instead of 3, saving lots of money. Okay. And then what they did is they didn't have horizontal well drilling technology then. So they had to drill all these wells right here. Okay? So this well here had a drainage shape that looked like that. That well there had a drainage shape that looked like that. That well there looked like that. So they had these odd looking drainage shapes looking like that. That was a geometric skin. That magnitude of that skin was around 1 to 2 to 3, depending how extreme it got. Okay, but that extra pressure drop maybe said you needed 1 extra well to get the same total production, but you needed 1 less platform. So it was a huge economic success, the design of this, what they called cluster development. So that basically you cluster all the wells around one spot, you get this convergent flow. It's non-ideal compared with equally spaced, but the effect is not a very large negative effect, and the added savings of having only 2 platforms instead of 3 was huge. So that's another flow geometry damage. But there's a number of these that I'm not going to go into, but there's others. Okay. And then mainly in the 70s, it did start in the 60s. People started thinking about trying to stimulate the permeability instead of it being going from 10 millidarcies to 2, bringing it from 10 millidarcies to 100. Okay? By putting acid, etching out, improving the permeability near the well. What would the consequence of that be up here? Okay? Well, basically, if you could stimulate it out, let's say even further than this, and you could increase the permeability. Oh shit! My car. I'm supposed to pick up my car. Okay, let me take this. All right. So what will happen is that if you get this permeability increase, the slope's going to get less. So now what we can do is stimulate out to here, okay, and now the pressure drop is negative, okay? Now the pressure drop is negative from where you would have been with no treatment to where you are. So in this case, the pressure drop, delta P, what we still call it skin, is negative. Okay? Consequently, the skin itself is negative. Okay, and we've got that 8 number, and now we're subtracting something. So how negative can this get? Okay? So we can have stimulation skin, which can be on the order of -1 to -5. Okay? Okay, so that means that, remember, we're taking about 8 and we're adding the skin. That's proportional to our rate. Okay? So let's say that we're making 1 million standard cubic meters per day with a skin of 0. Okay? Constant 1/8. Okay? How much will we make? Now we've got the same constant, but now we're going to take 8 minus 4. We stimulate the well. Reasonable stimulation job is -4. Okay? It's going to bring it to 2, 10 to the 6th, right? Okay. So it doubles the rate for the same pressure drop. And theoretically it could go to tripling the rate. There's also other effects, but basically doubling the rate by stimulation is a good stimulation treatment. So this is and we also include this skin term here as well for stimulation. And then finally there's a stimulation flow geometry term, which is important. Flow geometry skin. Now, here I'm talking about, we've got a reservoir like this, and we're comparing with a well that's drilled vertical through here, perforated completely. Okay. And if now, instead of drilling that well, we're going to use the same equation. Okay. If instead of drilling that well, we drill pink well, it goes like that. Okay, with the length of the well being LW. And we started doing this in the 90s. Okay. This can lead to a skin on the order of -6 to -8. It just depends on the flow geometry. Maybe -5 to -7, but something on that order of magnitude. It's okay. Mainly a function of the length of the well. It's mainly a function of the length of the well and the K the permeability in the vertical direction to the permeability in the horizontal direction. If that becomes very low, then it has a hard time flowing vertically into the well. Okay? That's a bad thing. So it's this horizontal well skin factor is very much a function of the length of the well and the kVkh. This is the range for kVkh from 0.1 to 1. If you have a really low kVkh, if the vertical permeability is much lower, like a factor of 20 or 50 or 100 less than the horizontal, then this can actually become a positive skin. Okay? Because you basically just you're not able to drain the gas into the horizontal well. But that's an extreme case.
When this ratio is less than 1, it's going to be
It's all the ratio is always less than 1, basically.
In which case it's going to be skin?
It'll be something. It'll look something like this. You got 0, minus 10, plus 10. This is our horizontal. And let's just say the length of the well is 1,000 meters or something, or 2,000 meters. kVkh of 1, 0.1, 0.01, 0.001. Okay? So basically you're going to be down here. It's going to go gradually up here, but then as you get low enough perm, this thing is going to crawl up here and eventually become positive. I don't know exactly what it's going to look like. Maybe if it gets, something like that. I mean, the problem is that for it to be the horizontal well to be a good idea, you have to have vertical permeability. And here, going to the left, you're losing all your vertical permeability, so it's not a good idea. So, anyway, this is a kind of flow geometry skin effect in horizontal wells, and now they're very common, so you should be aware of it.
But we can make horizontal permeability artificially, like hydraulic fracturing.
No, but that doesn't change the permeability in the rock. It's only the local. That would only change the permeability. If you have a fracture, then the flow is going to be horizontal into the fracture. So, okay, the point is that the final equation here has got this skin in it. And we only have 4 minutes before I go pick up my car. Okay, but so I think we'll stop there.